The universe is a magical place, isn't it? It astounds us. It ignites our curiosity. For decades, we humans have been trying to understand our universe's true nature of reality. And we've come up with several brilliant theories and hypotheses, such as loop quantum gravity, quantum Einstein gravity, causal dynamical triangulation, and string theory. Out of all these theories, string theory is the most powerful and promising one. I think it's about time that we enter the amazing world of string theory. Before we understand string theory, we need to learn about the standard model of particle physics. The standard model is like a periodic table of physics that organizes all the particles in a comprehensible tabular format. These particles are called the fermions. They make up all the matter in the universe. The fermions consist of the quarks and the leptons. These particles are called the gauge bosons. They carry 3 of the 4 fundamental forces of nature: the weak force, the strong force, and electromagnetism. However, we haven't discovered a boson that carries gravity, the 4th fundamental force. Gravity is explained by Einstein's theory of special relativity, which states that gravity is just a result of curvature in spacetime. But the spacetime concept doesn't really fit in with the standard model. When physicists try to amalgamate the standard model with spacetime, their mathematics breaks down. String theory marries the standard model with spacetime. String theory hypothesizes that every particle, from a muon to a quark, is actually a microscopic piece of string. What distinguishes the different types of string or particles between each other is how they vibrate. Each different kind of string vibration defines a different particle. The way an electron string vibrates would be completely different to how a tau string vibrates, thereby differentiating between them. Strings can also represent the boson for gravity, solving the contradiction between the standard model and special relativity. Strings can be closed, or they can be open. The string can stop vibrating in one way and suddenly start vibrating in another, similar to a musical instrument playing a new note. In this way, a particle can transform from one type to another, for example, a quark to a muon, or even a quark to a boson. Strings are extremely small. The current estimate of the size of a string is 10 to the power negative 34 meters, inexplicably tiny. String theory also predicts objects called brains, spelled as branes, not brains. A brane is a two-dimensional membrane or analogous object in lower or higher dimensions. A zero brane is a point, a one brane is a type of string, a two brane is a two-dimensional flat sheet, and a three brane is a solid body, and so on. So far, so good. But here comes the problem. String theory requires at least 10 dimensions to work out. Truly, this is an idea that blows our mind. It's simply too hard for us to imagine. But maybe we just can't see those 7 extra dimensions. Maybe they're hidden. Nobody knows. Despite all these peculiarities, string theory is our best attempt to explain the true nature of reality. Yet, several questions remain unanswered. How do we travel through time? What came before the Big Bang? What is dark matter? We haven't answered these questions yet, but one day, hopefully, we will.